Assalamu alaikum students. In today's lecture, we will study the effects of retarding forces on the motion. Up to now, in many simple mechanics problem, we usually assume that a particle moves under an ideal forces only, such as gravity or an applied force. But in real motion, a body often experiences an additional forces that opposes its motion. This resisting effect changes the acceleration, the velocity, and even the total distance traveled. Today we will see how Newton's second law is applied when such retarding forces are present, and how this gives rise to more realistic equations of motion. In this lecture, our goal is to understand what a retarding force is and how it modifies a motion. We will write the equation of motion when a resistance acts on a particle, and we will see that in many practical cases the resisting force depends on the speed of the object. Then we will derive the equation of motion when the resistance is proportional to velocity. This will lead us to three important relations: velocity as a function of time, displacement as a function of time, and velocity as a function of displacement. Later, these ideas will help us understand more realistic vertical motion and the terminal velocity. A retarding force is simply a force that acts opposite to the motion of the body. The key word here is opposite. If the particle is moving upward, the retarding force acts downward relative to that motion. If it is moving to the right, the retarding force acts to the left. Because of this opposition, the force tends to reduce the speed of the particle. The examples shown in the figure are very useful. In the first case, a falling body experiences air resistance while its velocity is downward. In the second case, a projectile moving through air faces drag opposite to its direction of motion. In the third case, an object moving in a viscous liquid also experiences a resistive force opposite to its motion. So the idea is that retarding force is not tied to any one special system. It appears in many physical situations where a medium resists motion. Once a resistance is present, we must include it into the total force or the net force, such that the total force become the sum of the gravitational force and the retarding force. This means that we no longer are dealing with gravity alone. Newton's second law still works in the same way, but now the net force contains more than one contribution. The expression F equals f of g plus f of r tells us that the actual motion depends on the combined effect of the driving and resisting forces. Here, this f of g represents the gravitational force, usually equal to mg, where m is the mass and g is the acceleration due to gravity. The term f of r as a function of v indicates that the resistive force may depend on velocity, and that is an important idea because unlike gravity, resistance is often not constant. It changes as the speed changes. So as the body speeds up or slows down, the retarding force also changes. Here we have given a general mathematical model for an object under the influence of a retarding force. The force is written in a form proportional to a power of the speed. Let us understand each term carefully. The constant k is a positive parameter that tells us how strong the resistance is. A larger value of k means a stronger opposition from the medium. The exponent n tells us how the force depends on the speed. For example, if n equal 1, the force is proportional to the speed. If n equal 2, it is proportional to the square of the speed. Now look at the vector v vector over the magnitude. Now this is a unit vector in the direction of velocity. A unit vector has magnitude 1, so its job is to give a direction only. Because the force expression has a minus sign in front, the resisting force points opposite to the velocity direction. That minus sign is physically essential. It tells us that resistance does not drive the particle forward, it always acts against the motion. Here we focus on the two most common models. The first is linear resistance, where the retarding force is proportional to V. This is often used for relatively slow motion or for motion in certain viscous environments. The second is quadratic resistance, where the force is proportional to V square. This is very common in faster motions through air. The important point here is that the correct model depends on the physical regime. That means we cannot assume one formula for every case. At lower speeds, the force may increase roughly linearly with speed. At higher speeds, it often arises much more strongly, and then the quadratic model becomes more realistic. So here we have a connection between the mathematical form with the physical conditions. Here we introduce the aerodynamic drag, which is the retarding force experienced by a body moving through air. The formula shown is W equals half C of W rho A times V square, where this symbol C of W is the drag coefficient. It depends on the shape and flow conditions. The symbol rho is the density of air, so denser air produces larger drag. The symbol capital A is the cross sectional area, meaning the effective area exposed to the air, and of course this symbol V for the speed. Notice the dependence on V square as discussed on the previous slide. That means if the speed is doubled, the drag does not merely double, it becomes 4 times larger. And that is why air resistance become especially important at higher speeds. The application box shown here is also useful. For example, in ballistics, aerodynamics, sports motion and vehicle design, drag is not a minor correction. It can strongly control the trajectory and performance of the moving body. Here we combine a force diagram with graphs. In the projectile sketch, the force W is the drag force, and it acts opposite to the velocity. The force F of G acts downward due to gravity. The diagram also shows a force L of alpha, which is a left-like force perpendicular to the drag direction. This reminds us that aerodynamic motion can involve more than one resisting effect. The point marked as D is related to the center of pressure, such that if the center of pressure does not coincide with the center of mass, then a torque can be produced. which affects the stability of the projectile. So the figure is not only about force magnitudes, it is about rotational effects as well. Now the graphs on the right side here shown, one graph shows that the drag coefficient varies with the Mach number, so it is not always constant. The other graph shows that air resistance increases with velocity, and near higher speed regimes the rise may become very rapid. So the important point is that the realistic aerodynamic motion is speed dependent. It is also geometry dependent, and sometimes it is quite complex. Now we simplify the problem and move to a one-dimensional horizontal motion with a retarding force proportional to velocity. This is the simplest mathematical model of resisted motion. Newton's second law is written as ma equals m dv by dt, which is also equals to minus k m times v. The term dv by dt means rate of change of velocity with time, which is acceleration, and this minus sign again tells us that the force opposes the motion. Now if we divide both sides by m, we get dv by dt equal minus k times v. Now this is a differential equation of the form where an unknown function is present along with its derivative with respect to time. Here the unknown function is the velocity as a function of time. The equation says that the rate at which velocity changes is proportional to the velocity itself, but negative in sign, so larger speed means stronger retardation. Here we have given the physical picture for the one-dimensional model. The body is moving along the positive x direction with initial velocity v naught. The resisting force acts in the opposite direction. So even though the particle is moving forward under the influence of resistive force, and this gradually reduces the speed. The figure is taken from the course book, and it converts the equation into a physical picture. The motion is horizontal, so gravity is not the main focus here. The important point is that the surrounding medium opposes motion continuously, and the particle does not stop instantly. Instead, it slows gradually, and that gradual slowing is exactly what the differential equation on the previous slide describes. Now we solve the differential equation starting from dv by dt equals minus k times v. To solve this, we separate variables such that we gather all terms involving v on one side and all terms involving time on the other side. That gives dv divided by v equals minus k times dt. Next we integrate both sides, and on the left side the integration of 1 over v times dv gives us log of v, and on the right side the integration of minus k times dt which is the integration of minus k giving us minus k times t plus a constant of integration. Then we apply the initial condition v of 0 equals v naught as given in the problem statement, which means at time t equals 0 the particle has initial velocity or speed v naught that allows us to determine the integration constant. And finally, we obtain velocity v uh, equals v naught times e to the power minus k times t. Now, this is an important result. It shows that the velocity decays exponentially with time. Exponential decay means that the speed decreases rapidly at start and then move gradually. It never drops abruptly to zero. Instead, it approaches zero asymptotically. Now that we calculated velocity as a function of time, next we can find the displacement. Since velocity is dx by dt, we write dx by dt equals v of naught e to the power minus k times t. Then we integrate with respect to time to obtain the position. After integration and applying the initial condition x of 0 equals 0, we get the expression for the displacement, which shows that the position continues to increase with time, but the increase becomes smaller and smaller because the particle is slowing down. Now look at the limiting behavior. As time becomes very large, the exponential terms e to the power minus k times t tends to 0, and therefore the x approaches a constant term v of naught divided by k. That means the particle travels only a finite total distance in this ideal model. Even though the motion continues mathematically for all time, the displacement approaches a fixed limit. So the retarding force eventually removes the motion so effectively that the particle practically comes to rest after a finite distance. Here we develop another useful relation, this time between velocity and displacement directly. We use the chain rule from calculus. The chain rule allows us to connect derivatives with respect to different variables. Here we write dv divided by dx equals dv by dt into dt by dx. Since dt by dx equals 1 over v, and that gives us velocity with respect to x equals 1 over v times dv divided by t. After substituting the dv by dt equals minus k times v and following these simple mathematical steps, one can obtain the expression for the velocity, and this time as a function of position. So the velocity decreases linearly with displacement as evident from the above expression, and notice that the velocity decreases exponentially with time but linearly with position. Now this tells us that the same motion may look different depending on whether we describe it in terms of time or in terms of displacement. Here we discussed the physical meaning of the result obtained on the last slide. The equation F equals V naught minus K times X tells us that for every additional increase in displacement, the velocity drops by a fixed amount proportional to K. So if the medium is more resistive, meaning larger K, the speed falls more quickly with distance. Now this relation is especially useful when the position is easier to measure or when the problem given in terms of distance traveled rather than in terms of time. Also it is helpful to see that the motion under resistance is not described by one formula only. Depending on the variable of interest, we may write or use velocity as a function of time, or a position or displacement in terms of time, or we can express the velocity in terms of displacement. All these three described result are same physically, but the processes are different. And finally, these are the conclusion. A retarding force always opposes motion. In many physical situations, that retarding force depends on speed. Two common models are linear resistance and quadratic resistance. For the linear one-dimensional case, the equation of motion gives exponential decay of velocity. The displacement approaches a finite limiting value and velocity decreases linearly with time. Now, these results form the foundation for a more realistic motion in fluids and air. In another word, these results are important for understanding free fall, projectiles with drag, motion in viscous media, and many real engineering and physical systems. These are the assignment questions. The first question focuses on vertical motion with a retarding force proportional to velocity. That takes the one-dimensional idea discussed in this lecture further by including gravity as well. The next question move towards a projectile motion and air resistance, showing how the same concepts become more realistic and also more challenging in two dimensions. The students should consult chapter 2, especially example 2.5 and problem sets at the end of the chapter. And thank you everyone for your time.